Hello all and welcome to Physics with Pranav. If you're new here, I'm Pranav. I really enjoy physics and I really enjoy teaching others the topic. I used to be a tutor for students across the world who were doing IGCSE physics as well as AS and A-level physics, and I helped them achieve really good grades. I did the curriculum myself when I was back in school, and I was an IGCSE world topper in science back in 2013. My hope from this channel is to provide you with the methodology, the tips and the tricks that help me and my students achieve excellent grades in their exams. And I essentially use a consistent approach, which is the same approach I use when I prepare for the papers. So first, I prioritize the key topics in each chapter. So although, yes, the general advice absolutely is to thoroughly read everything that shows up in your textbook, if you were to prioritize your time to focus on some of the topics, it's important to know which ones are commonly tested in the most recent papers. So I have essentially gone through the research for you between 2020 and 2022 to identify the topics that are most commonly tested topics from each chapter in the past papers. And once we've done that, the next step is to solidify the foundation. So once we know what the key topics are, it's important that we understand the key topics. So I dive a little bit deeper into those. And the final prong is obviously to be able to practice questions from those key topics with actual past papers. So in a previous video for the second chapter of the CAIE IGCSE curriculum, which is motion, I looked at some of the most commonly tested topics, and I also dove a little bit deeper into them to give you like the solid foundations. In this video, the focus is going to be more on looking at past paper questions, where I'm going to be solving some of these questions with you just to make sure that the concepts that are tested is clearly understood. So without further ado, I'm going to dive into the papers. Perfect. So I'm going to start with paper 2 and then I'm going to move to paper 4. I've generally arranged the papers in the reverse chronological order. I do want to say that for the paper 2s, my general approach is to solve all of the papers in the most recent year. So this would be 2023, which is the last year. So all the papers in 2023, I've solved those for paper 2, and I would pick out a few papers from previous years where I think there have been some really interesting questions that are worth looking at. And then we will move to paper 4. So in paper 4, I think I'm a bit more selective, so I don't do all the papers from last year. But what I do instead is I go through papers from 2020 all the way to 2023 to see if there's any really interesting questions that are worth looking at, which also reinforce the concepts that we looked at in the previous video. So if I were to do a quick refresher of the key tested topics in this chapter, we have essentially calculations, and they can be formula-based calculations or graph-based calculations, where you'd have to calculate the quantities of either distance, displacement, speed, velocity, or acceleration. And the other commonly tested topic is the description of how these different quantities change in different scenarios. So I did say that the most commonly tested topic is the graphical side of things, where you have to use graphs to be able to calculate or to plot these different quantities. The second most common being the formula-based ones, at least for the multiple choice paper, which is paper 2. And after that, the most common topic that we will be looking at is the description within chapter 2 motion. So if we dive a little bit deeper, starting again reverse chronological order, so we've got paper 2-3 from October, November 2023. So I'm just going to go down. I'll also say this, that I'll only be focusing on the questions that are pertaining to this topic. So I do appreciate that we well, there's around 40 questions in this paper, so we'll not be looking at all the questions, but we'll be looking at the questions pertaining to this topic, so bear with. So the first question, you'll usually find questions pertaining to the topic of motion within the first sort of 5 questions generally. So the first question is about, so it says a train is on a straight track. The graph shows how a quantity y varies with time. So you've got a quantity y, which we don't know what it is, and this quantity is varying with time, but it doesn't really change at all. So the question they're asking is which statements can be true. So for the statements kind of questions, one thing that I really like to do is I like to first eliminate the statements that are definitely wrong, right? So if I start off with the first one, they've said the train is stationary and y represents the distance from the last station, right? So this statement, yes, can be true. So if you had distance there, or if you had displacement there, and if that didn't change with time, then essentially, the object is stationary, and that would represent the distance from the last station. So yes, that is a true statement. The next thing is a train is moving, and y represents the distance from the last station. So if y is the distance, then a straight line with no gradient means that the train is at rest, right? So the train cannot be moving, so that statement is false. The next statement is the train is stationary and y represents the speed of the train, right? So if y was the speed, you can see here that this line without no gradient is going to show the object moving at constant speed. Now there is a scenario where you can have a straight line with no gradient in a speed time graph, and that is showing that the object is at rest. But that is when the speed is 0. So you're going to have essentially the straight line lying on your x-axis or your time axis. But here, there's clearly a value that the speed has. So the train cannot be stationary in that situation. So 2 and 3 are wrong. And you don't really even have to look at 4, because we can see that they want to see which combination of statements is true. You know that 1 is true, you know that 2 and 3 are wrong. So 1 and 2 can't be right, 2 and 3 can't be right, and then 3 and 4 can't be right. So 1 and 4 is the right answer. So I would try and use that process of elimination. So if you go to the next one, the diagram shows a speed time graph for a moving object. So you got a speed time graph, and the first thing that I would like to make you recollect is the different gradients that we saw for the graphs, right? So we'd seen for speed time and velocity time graphs. What we've essentially got here is we've got a positive, non-linear, flatlining gradient. So what do we mean by positive, non-linear flatlining? So if it's positive, there is an acceleration, right? If it's non-linear, then the acceleration is changing. And if it's flatlining, then it's going to a constant speed. So that's essentially the 3 things that we know from the notes that we looked at before. Now, well, if we look at the options, B is definitely not true because the speed is not decreasing. D is not true because, for constant speed, you're going to have a line without a gradient, you're going to have a flat line, and this line clearly has a gradient, has a slope, and the slope is changing. The fact that the slope is changing means you can't have constant acceleration, because if it's a changing slope, your acceleration changes because the slope of a speed time graph is the acceleration. So, well, even if you went through the process of elimination, you would have decreasing acceleration. But I think for questions like this with the graph where they're asking you to describe it, I think the easiest thing is if you can remember the notes from the chapter. And again, there is a link for that video below if you want to go revisit it. So let me see if there's any more questions pertaining to this topic. Okay, I think not. So if you move to the next paper, so this is again October November 2023, but we're looking at the 22 variant. So again, if I went down and, so the first question talks about scalar quantities vectors, which I suppose we can answer because we looked at it a little bit. We do know that acceleration, velocity, and force are all vectors, because they all act in a direction. We know that time is a scalar, so time only has, technically time has a direction, but at least for GCSE physics, you know that time essentially only has a value. So we move to the second question. A student measures the average speed of a cyclist in a race. Which quantities must she measure? So again, for this, where you're trying to describe stuff, try to use the process of elimination. How can I eliminate some options fairly quickly? So if I want to find the speed, I want to know the distance and I want to know the time, right? So which quantities must she measure? The total time taken to complete the race. Yes, she would have to measure that. And the time taken for the cyclist to reach her highest speed. So here you just got 2 times, there's no distance. That's clearly wrong. The next one is the total time taken to complete the race. Yes, she does need that information. And the total distance traveled by the cyclist at her highest speed. Now, it's easy to get confused by this because you've got a time, you've got a distance, a total time, total distance. But we want to know the average speed of the cyclist. We don't want to know, the distance that they traveled, during the highest speed. We want to know the distance they've traveled in total, right? So that's how we're going to get the average, because the average speed is the total distance by the total time, right? So it can't be B. If we look at C, it's the total time taken to complete the race and the total distance traveled by a cyclist. That's the correct answer. Usually, if you're very sure of it, I wouldn't even bother going down further to read the other ones, but it's always a good idea just to check in case there is a better option, right? So indeed, they said the time taken to reach a high speed and the total distance traveled by the cyclist. Again, this is sort of the reverse of B, where I think they're trying to find the time to reach the high speed. but they've got the total distance traveled. So you don't want that. You don't want the highest speed. You want the total speed and the total distance. The next thing, the next question goes: the diagram shows a series of images of a moving object taken at regular intervals. The object is moving from left to right. So these are, snapshots of an object moving, and they're clicked at regular intervals, right? So every second or every few seconds or something like that. And you can clearly see that initially the object is moving at a constant speed because the distance between the time intervals is the same, and the time interval is always the same. That's what they're saying by regular intervals. But you can see that, as you move from left to right, you can see that after sort of the sixth dot, the distance just keep increasing, which suggests that the object is covering a higher distance over the same time, right? Which means its speed is increasing, which means it's accelerating, right? So the first statement says the object accelerates continuously. That's not true, because in the first, whatever the interval was for the first 6 dots, the object is not accelerating. The object is clearly not decelerating, because if it's decelerating, the gap between the dots needs to reduce for the same time interval, but it's increasing, so it can't be decelerating. You've got another statement on deceleration here, so that's clearly wrong, which leaves us with this option. But then let's read this option. The object travels at constant speed and then accelerates, which is correct, because it travels at constant speed and then after that it does accelerate. So that is the correct answer. I'm just going to quickly check again if there are nope. So these go into some of the topics we'll be exploring later. So moving on, yeah, these are fun. These are going fairly quickly. So October number 23, we got variant 2-1. So again, we got a question on vector quantities. I'd say vector quantities more on chapter 1, but if you were looking at it, essentially, density, mass, all of these tend to act in a direction. Weight is a force, so that tends to, but weight is a force, so weight will be a vector. So that is the vector quantity there. The other ones, they only tend to have a value. They don't tend to have a direction, so they would not be, vectors. They would be scalars. So if we do the next one, again, we've got a scenario where we've got a graph and we've got to try and describe what's happening. So which section of the graph represents a period when the car is accelerating, and it's a speed time graph. So you've got decelerating, sorry for reading that wrong. So you've got A, B, C, D. So there's 4 points on this graph. You can see that at A, it's a straight line with a slope, a positive slope, so it's a positive linear area. So that is an acceleration, that's definitely not a deceleration. At B, you've got essentially the acceleration is increasing till it reaches a constant speed. So B is not an area because that is again an acceleration. A and B, the gradients are positive, and the fact that it's positive means the speed is increasing. So it can't be A and B. At C, you've got a flat top, which means it's at constant speed. As time goes on, speed doesn't change, so it leaves us with D. And that makes sense because that's negative linear. Again, if you look at the video I made on the content, you'll be able to know that, yep, negative linear, which means for a speed time graph, that is a deceleration, a constant deceleration. If I look at question 3, an object reaches terminal velocity after being dropped and falling through the air. Which graph shows how its speed varies with time? So we know that if the object reaches terminal velocity, we are expecting a flat line at the end. But that doesn't really help us in this scenario because technically all of these graphs have a flat line, in the end. So you can't really use that as a clue. And essentially they want to know how its speed varies with time. And the thing is, we've seen the graphs on freefall. We know that the object keeps accelerating, but its rate of acceleration slows down, right? So it's not falling with a constant acceleration. So that would be the case if the object was dropped and there was no air resistance, but they've said the object is falling through air, so that's not right. That leaves us with B, C, and D, right? So in the case of B, we know that is essentially a positive non-linear rising gradient, which means the speed keeps increasing and then it becomes constant. That's not true. The speed keeps decreasing and then it becomes constant. We know in the case of D, that shows an object that is decelerating and then has a constant speed. That is not true because when an object falls, again, without a parachute-assisted fall, it is going to be accelerating initially. So that leaves us with C. C gives us the right profile of a falling body, which reaches terminal velocity. So again, you'll see that in most of these papers, by like sort of question 5, you would have done both your questions on the topic of motion. So if you're feeling very confident in the topic, then I would definitely look at the start of the paper. Okay, so we are looking at May-June 2023, and we've got paper 2-3. And we start off with a nice calculation question. So in a calculation question, I think I always start by asking, what do I know? What is given and what do they want, right? So what is given is a speed time graph, yeah, and you've got the values for the speeds and the times, and they want to know how far does the object travel at constant speed. So they want to know distance, right? And they want to know the distance only for the section where the object travels at constant speed. So first thing that you want to do is, okay, so if you want to find the distance in a speed time graph, you need to find the area under the graph, yeah? So that's the first thing that you need to ask yourself and confirm. The next thing is, well, which area are they interested in? Are they interested in the total area? Are they interested in the area where the body's accelerating or decelerating or constant speed? So we know they want the area of constant speed. How do you know constant speed? You know constant speed when in a speed time graph, you've got a flat line with no gradient. So that line there at 5 meters per second is a flat line, and that is where the object is traveling at constant speed. So they want essentially the area of this rectangle, right? And the area of this rectangle is going to be its length multiplied by its breadth. We know that the length is 15 minus 5, that's going to be 10. The breadth is going to be 5 essentially, 0 to 5 or 5 minus 0. And then if you multiply those together, you get a value of 50 meters. So usually the calculations in multiple choice papers are fairly straightforward. It's stuff that you can do essentially without a calculator, but I would always recommend still carrying your calculator with you to the exam. So that's the first question. Nice graph calculation based question. So second question goes, which statement about a falling object accelerating close to the Earth's surface is correct? Right? Okay, so you got a falling object accelerating close to the Earth's surface. So this question is coupling chapter 3, and we will be looking at chapter 3 as well, where we will look at the content. But I have described what happens in chapter 2. And the reason I say this involves chapter 3 is because you're looking at forces, and we haven't really covered forces in chapter 2. But the key to be aware of is that in most of the papers in your GCSEs, especially so in your AS and A levels, you are going to have a mix of concepts being tested in the same question. So it's not just going to be one concept and boom, that's it, you're done. You're going to have a few different concepts being tested, right? So again, if we go through the process of elimination, because this is a description-based question, if we start with A, it says the weight of the object is increasing and the force of air resistance on the object is decreasing. Now, this is not true. As we'll see, the weight depends on the mass and the gravitational acceleration. So near the surface of the Earth, the gravitational acceleration is constant. The mass is the amount of matter something has, and that is constant as well. So the weight cannot be increasing. Therefore, that statement is wrong. The second multiple choice looks at the weight of the object and the force of air resistance on the object are of equal magnitude but act in opposite directions. So if you think about it, the weight of the object and the force of air resistance on the object are of equal magnitude but act in opposite directions. They definitely do act in opposite directions. The weight pulls the body downwards, the force of air resistance pushes it upwards. But if they are of equal magnitude, the net force acting on the object is 0. And if the net force acting on the object is 0, that means the object is not accelerating. Again, as we'll see, force is the product of mass and acceleration. And essentially, if there's 0 force, then either mass or acceleration has to be 0. And most objects tend to have a mass, unless they are like some subatomic particles, but even they tend to have very tiny amount of mass. So yeah, so that usually means there is no acceleration, but they've said the object is accelerating, so that can't be right. So C says the weight of the object is constant, which we've seen is true, but the force of air resistance on the object is increasing. And this is true as well. As the object falls, what tends to happen is the force of air resistance increases till, as I said in point B, both the forces are balancing each other and acting in opposite directions, which means the object falls without an acceleration or at constant speed. So this is what tends to happen. And the last one is the weight of the object is less than the force of air resistance, which can't be true because then the object would be decelerating. It wouldn't be falling towards the Earth, rather it would be getting blown away from the Earth, which doesn't happen unless the person's got a parachute, but they're talking about free fall, right? So C is the correct answer here. Now, if you look at question 3, So we've got 3 questions in a row. So an aircraft is moving at 60 meters per second in a northerly direction. So it's moving towards the north at 60 meters per second. Okay. When a crosswind from the east starts to blow and the speed of the wind is 13 meters per second, they want to know the magnitude of the aircraft's velocity when the wind is blowing. So they want you to calculate the resultant velocity. So we have seen this concept. And the thing is, well, essentially to know the resultant, you've got to be able to draw a little arrow. Here, usually in paper 2, you're not going to be having any scenarios where the two sort of vectors that you need to add together are not perpendicular to each other, right? In most scenarios, or almost, I can almost say in 100% of the scenarios in paper 2 at least, they are going to be at right angles to each other. So you can just use Pythagoras, right? So you've got 60 meters per second, head to toe, and you've got 13 meters per second, and then you've got a resultant velocity which starts from the toe of the first vector and goes to the head of the second. And it makes sense as well, because if you've got a northerly wind and an easterly wind, then you've got to be moving in the northeastern direction, which is the direction which the arrow is pointing. So that makes sense. And if we used Pythagoras here, so that's going to say the resultant velocity square is going to be equal to the sum of the square of these component velocities, which is 60 squared plus 13 squared. And then once I add the squares of those and square root the answer that I get, that will give me an airspeed of 61.4 meters per second, right? And rounding that up, that would be 61 meters per second. So that is a nice resultant velocity question. So yeah, again, most of these other questions are not from this topic, so moving on. So if we go to May, June 2023, we look at paper 2.2. So I've got a question here saying a light ball is held at rest at the top of a tall cliff. It is released and falls through the air, eventually reaching its terminal velocity. So which row describes the behavior of the ball as it descends? So the first thing is, we know it's reaching its terminal velocity, which means it's a constant velocity. So the final acceleration has to be 0, right? So again, using my concept of elimination, B and D are wrong because they've got an acceleration of g, but at terminal velocity you have no acceleration. And we know that objects near the surface of the Earth fall at the acceleration of g, which is the acceleration due to the gravitational force acting on the mass of the object. Again, we'll be looking at this in the chapter on forces, which is the next topic. And again, as I've said, these papers sometimes tend to combine concepts together, but we're just trying to, I suppose, single out the questions most related to this topic. And in this case, well, the answer is C, because the initial acceleration is g, which is the acceleration due to gravity acting on the mass of the object, and the final acceleration is 0 because there is no terminal velocity. So that is how you would approach that question. We've then got a question on graphs. The graph represents the motion of an object, of a car. So you got a speed, you got a time. Speed time graphs, as I said, most common type of graphs. How far is the object moved between 0 and 5 seconds? So how far, they want you to calculate the distance. And they want you to calculate the distance between 0 seconds. Unlike the previous paper we saw where you had to find out where the area was for the constant velocity, here they're just saying calculated between 2 times, which is a little bit easier. So they say it has to be from 0 to 5 seconds. So again, if we looked at the area under the curve from 0 to 5 seconds, we can see that we essentially got the area of a triangle. So that's half base into height, half into base, which is 5, into height is 10. So that gives you a value of 25 meters. So that is the value there. Again, it's a fairly straightforward question. Hopefully there's no confusion, as long as you know how to calculate different quantities from a graph. So if you look at May, June 2023 and we look at paper 2.1, we go down. The second question says, an object falls towards the surface of the Earth. The object is falling at its terminal velocity. Which statement is correct? So again, let's use the process of elimination. There is air resistance and the acceleration of the object is is negative. So that is not the case when an object is falling with terminal velocity. When the object is falling with terminal velocity, there should be no acceleration, negative or positive. So if you look at questions, if you look at options A and C, you can see that they've said the acceleration of the object is negative. There is no acceleration, it needs to be 0, so A and C can't be right, which leaves us with B and D. If you look at B, they say there is air resistance and the acceleration of the object is 0, and D says there is no air resistance and the acceleration of the object is 0. Now when an object falls at terminal velocity, air resistance is still acting on the object. It's just that the air resistance balances the force of gravity on the object. So the option is B. D is not correct. So if we go and then look at the next question, question 3, so we got again two questions in a row. So here we got a speed time graph, the classic graphs that we typically get, and then they want you to calculate the distance traveled by the vehicle in 400 seconds. Again, very similar to before, where they've told you to calculate the speed between 2 points in time. You've got a nice little triangle here. So again, you'd have the distance is the area under the curve for a speed time graph, and distance is half base into height. So base is 400, height is 20, half of that. So you get a distance of, 4,000 meters, which is what I've selected here. So that's the question on that. If we move to Feb-March 2023, and you only got 2 variant for the Feb-March papers, which is the 2-2 variant. Sorry, you only got 1 variant, and that's a 2-2 variant. So if you go down, the first question is the diagram shows a speed time graph for a car. You can see that they marked 2 points X and Y, and they want to know what is happening at X and Y to the car. So speed time graph at X is essentially on a positive linear slope. So if it's on a positive linear slope, that means that if it's positive, it's accelerating. If it's linear, the acceleration is constant. So if it's accelerating, its speed is changing, which means essentially it's got to be C or D. It can't be A or B. And then if you look at Y, it's a no gradient scenario on a speed time graph. So that is essentially just an object that is moving at a constant speed. So we already eliminated A and B. So if C is not correct because point Y is not at rest, then the object at X is moving with changing speed, and then at Y it's moving with constant speed. So 4 objects are moving in a straight line. The table shows the distances moved by each object in each second of its motion. So it's quite similar to the question with the, with a flashlight, taking snaps at regular intervals of an object that's moving. But except here they haven't got like an image, instead they've got like, say, a table of the data. Which object is moving with constant non-zero acceleration? So we want an object whose distance is increasing every second. So if you look at that, in the first case, it's all 5s. If it's all 5s, that's constant speed. And we want something that's essentially, we don't want it slowing down. So in none of these cases is the body slowing down, so that's fine. So if you look at B, you can see that it's moved 5 meters in the first second, 6 meters in the second, 7 meters in the third, 8 in the fourth. So it's moving a constant, it's increasing its speed by a meter every second. So its velocity is increasing by a meter every second. So that is a constant acceleration scenario. But if you just look at the others, if you look at C, it's increased by 2 meters per second in the second. It's increased by 3 meters per second in the third second, and 4 meters per second in the fourth second. So that's not correct. And then if you look at the in option D, it's increased by 3 meters per second in the second, by 6 meters per second in the third second, and by 12 meters per second in the fourth second. So the thing is, A is moving at constant speed. C and D are accelerating, but it's not a constant acceleration. So B is the right answer, where you've got a constant non-zero acceleration. So again, all of these questions are based on future topics. So that, I think, brings us to the end of the 2023 paper 2s. Hopefully all of that made sense. We will now dive into paper 4, but feel free to pause the video here for a short break. Assuming you've had your short break, coming back, let's have a look at paper 4. So I picked May-June 2023, I picked paper 42. So May-June 2023, paper 42, got a question here, which talks about equilibrium and gravitational potential energy. So that is definitely, those are not topics that we are discussing, but again, as you will see in all these papers, you have concepts that check, essentially you have questions that check different concepts. So if you look at 1A, part 1, you can see that checks for the concept of equilibrium, which is a few chapters from now. If you look at the second question, that's more around like gravitational potential energy, whereas the third question focuses on an object in free fall, and that is stuff that we've done in the in chapter 2. So we've got, essentially they've said Figure 1.2 shows a vertical speed time graph for a parachutist who jumps from a stationary hot air balloon. Yep. They say the parachutist jumps from the balloon at time t equals 0 and reaches the ground at B. The point A indicates where the parachute opens. So on figure 1.2, label a point on the graph where the acceleration is 0 with 1, negative with 2, decreasing with 3. So if you want 0 acceleration, you've got to be traveling at constant speed, right? And constant speed happens around here because you've got a flat line with no gradient, and happens around here. So I've just selected this point there. So that's point 1. Apologies for the slightly misaligned arrow, but that is essentially point 1, this portion here. Negative with 2. So if you want to have negative acceleration, you need to have a negative gradient. So there's only this point really with a negative gradient. So that is 2. And then if you want to have an object with essentially decreasing acceleration, but there's still an acceleration nevertheless, you want an area with a positive nonlinear flatlining gradient. So this is one of the curves that we've seen in our chapter notes. So here you've got a positive gradient because there is an acceleration. It's nonlinear, which means the acceleration is changing. And how is it changing? It's decreasing because it's going up to a constant speed. So that is point 3. The second question is an explanation question, which says, explain in terms of forces the changes in motion which occur from when the parachutist leaves the hot air balloon until point A. So here, again, it's a merging of the concept of forces, which we'll look in chapter 3, and what we've studied about the motion of objects, which is chapter 2. But I will explain it nevertheless because we have covered the concept of an object in free fall. So we can see that when the parachutist jumps from the hot air balloon, gravity acts on their mass and air resistance acts on their surface area, which is true. Then the gravity pulls them down and air resistance arrests this motion. So essentially it's trying to push them up, to prevent them from, essentially it's opposing the direction of motion. During the initial phase of the fall, the gravitational force is greater than the drag force, resulting in a downward acceleration, which is this region here. And we're then saying, however, as the parachutist continues to fall, the upward drag force increases till it eventually equals a downward gravitational force. So if you look, this is what I mean by positive nonlinear flatlining. So the drag force catches up with gravity, slowing the object down until it reaches a constant velocity. And then we've said at this point the net force on the parachutist is 0 when they reach terminal velocity, because when an object is traveling at a constant velocity, there is no force acting on it. There's no net force acting on it, rather. So at this point, the net force on the parachutist is 0. Therefore, they have no acceleration and fall at a constant velocity, also called the terminal velocity. So that is what happens up to the point A and is marked by 1. So yeah, that was the concept from this topic that is tested in this paper. Again, it combines a bit of the forces chapter, but yeah, that is typically inevitable in these papers. Now we're looking at May-June 2023. We're looking at paper 4.1. So here you've got the very first question is a classic question on calculating vectors, being able to calculate resultant vectors. So this is again a topic that is quite common. So if I look at this, we've got figure 1.1 shows a straight section of a river where the water is flowing from right to left at a speed of 0.54 meters per second. That's that. A swimmer starts at point P and swims at a constant speed of 0.72 meters per second relative to the water and at right angles to the current. So at right angles to the current, the current is flowing that way, and he's swimming relative to the water and at right angles to the current. So he's trying to flow up like that. Yep. So they want us to determine relative to the riverbank. So the horizontals above and below the river is the riverbank. Both the magnitude and direction of the swimmer's velocity. This is your classic question on vector addition. And it's typically 4 marks. So the way you would do it is I'd started off with the speed of the swimmer. So swimmer is swimming at 0.72 meters per second. He's swimming sort of upwards. So we've got that arrow pointing up. And we know the head to toe rule. So the head of the first arrow showing the speed of the swimmer has to be linked to the toe of the second arrow, which shows the speed of the current, which is again 0.54 and it's constant. So we've got that. And the resultant arrow starts from the toe of the first vector and goes all the way up to the head of the second vector. So that's the resultant velocity. And that makes sense because if this guy starts off here and he's swimming that way, he's swimming upwards, and then there is a current that's flowing from right to left, then he's kind of going to be going upwards still, but more to the left, which is what this is showing, this resultant velocity. So again, because the vectors are at right angles to each other, I would just use Pythagoras theorem. So we're trying to find the magnitude of the resultant velocity. So the square of the resultant velocity is equal to the sum of the square of these two velocities, which is 0.54 squared plus 0.72 squared. And then when I square them up, add them together, and take the square root of the answer, that gives me a resultant velocity of 0.9 meters per second. So the other thing as well is, if you're a math student, the easy thing to do would be to use a bit of trig, because again, you've got a right angle triangle. So I'll quickly, which is what I've done here, and I'll quickly just describe what I've done. So the tangent ratio from trigonometry, you can find the angle to the vertical. So they want you to find essentially this angle here. So there's an angle there. That's the angle that they're interested in, because that's the, that's not the angle they're interested in. They are interested in the angle to the vertical, right? So the angle to the vertical is essentially this angle there. Yep, so it's the angle between the velocity of the swimmer and the resultant velocity. And the way to calculate that would be to first calculate the angle between the resultant velocity and the bank of the river. So one of the ways, so you could calculate that, or you could calculate this. So it's fairly straightforward. So if I am looking at the angle to the vertical, that is essentially this angle here. If I'm looking at the angle to the bank, that is this angle there. So I can calculate the angle within the triangle first. So one of the ways to do that is use the tangent ratio. So the tangent ratio says that the tan of this angle, which we're interested in, is equal to the ratio of the opposite side and the adjacent side. So in a triangle, in a right triangle, the opposite side is the easy bit. That's the side opposite to the angle. The adjacent side is essentially, so you've got two sides that are adjacent to the angle technically, but then you've got the long side, which is always the resultant velocity, and that is called the hypotenuse in a right angle triangle. So the adjacent is always a side that's adjacent to the angle, but that is not the hypotenuse. So that's going to be the 0.72. So if you take a ratio of that, and then we do what's called the tangent inverse to be able to calculate the angle, we will find that the angle from the vertical is around 36.9 degrees. And then if you wanted to find, essentially they want to know relative to the riverbank, so that is the blue line here, they want to know the angle relative to the riverbank. So that is the angle there. Yeah, so we know that the swimmer is swimming perpendicular to or perpendicular relative to the stream. So this entire angle will be 90 degrees. Yeah, this entire angle will be 90 degrees. We've just calculated this angle here using a bit of trig. So the angle there is just going to be 90 minus the angle inside here. So that is essentially 90 minus 36.87, which gives me 53.13. So I've included up to 2 decimal places. I believe your paper expects you to include up to, well, there is no, there's essentially, I would say 3 significant figures is generally what is acceptable. So I would tend to include it to 3 significant figures, in which case this would be 53.1 degrees. So this is how you would do it with Pythagoras and with a bit of trigonometry. The other way you can do it is obviously using a scale drawing. So you could take 1 centimeter equals 1 meter per second. Then you would have a line which has a length of 0.72 centimeters. You would have another line which has a length of 0.54 centimeters. And then, if you joined it up with the resultant velocity, all you need to do is take your ruler out to be able to measure the length of that velocity. And you would then have the magnitude of velocity there. And if your drawing is to scale, you can just use a protractor with the center of the protractor here, and you would be able to get the angle between the resultant velocity and the bank. So that is, it's probably, the scale drawing is probably easier if you wanted to find the angle and if you're not comfortable using trigonometry. But again, with right angle triangle, especially if you're a math student, I would recommend using Pythagoras and trigonometry just because it's a lot quicker. You can just punch some numbers into your calculator. The second question is, after 1.5 minutes, the swimmer reaches point Q, okay? So they haven't shown where point Q is. It could be anywhere in the river really, but it's after traveling 1.5 minutes. So I want to calculate the distance between P and Q. So I think with these calculation questions, I always ask myself, again, what is given and what do I need to find? So I know the speed of the swimmer. So speed of the swimmer is 0.9 meters per second. And I know the time, that's 1.5 minutes. So obviously I need to make sure the units are all the same. So if that is at meters per second, then I need to convert minutes to seconds. So that would be 1.5 times 60, which is what I've done here, to be able to get the total time. And then I want to be able to get the distance. Now, if you remember the little triangle that we looked at for relations between the quantities, the distance is on the top, and then you've got your speed and the time at the bottom, which means if you want to get the distance and you've got speed and time, you need to multiply them together. Yeah. So distance equals speed into time. I've got my speed as the answer from the previous question. And then I've done my time conversion from minutes to seconds here. And if I multiply that all together, I get a distance of 81 meters. So basically, the swimmer has swum a distance of 81 meters in 1.5 minutes at a speed of 0.5 meters per second. So not bad at all. I'm just trying to see if there's any other sort of questions. Nope. So looks like that is essentially the key question related to this topic from this paper, which is May-June 2023, paper 4.1. And now I've got October-November 2021, paper 4.3. So here we've got a question where I'm required to find a few things from a graph, as well as maybe plot some points on a graph. Let's see. So we've got a ship sails in a straight line between two ports. Figure 1.1 shows the speed time graph of the ship for the first 100 minutes of its journey between the two ports. So you got first 100 minutes, you got time in minutes, you got the speed in meters per second. So it's obviously different units. You got to keep in mind to convert either the speed to meters per minute or the time to seconds. So they want to calculate the maximum acceleration during the first 100 minutes of the ship's journey. So the first thing, again, with these calculation questions is to ask yourself, what do I know? So I've got a speed time graph. If I want to calculate the acceleration, I need to calculate the gradient, right? And if I want to calculate the maximum acceleration, I need to look at the point with the maximum gradient, right? So that is what I need to calculate, right? So that's what I need to calculate, and this is the information that's given to me, right? So when I look at this curve, obviously I've put in bold green the area with the maximum acceleration, but it makes sense because the acceleration is a slope. So if you're looking at the maximum slope, you can see that if I were to draw tangents or tangents of points that touch a curve at just one point and try and find the gradient, they're like quite, it's initially quite flat, and then it gets, more and more and more slopier. And we can see here that this is the point. The green line is a point where you've got the maximum gradient. So that is also the point with maximum acceleration. If I wanted to calculate the gradient, I want to find the change in the y values, i.e. the change in the speed values, divided by the change in the x values, or the change in the time values. And the other thing to keep in mind, of course, is, if I want to find the change, I need to be able to pick 2 points. So I have picked the points t equals 40 minutes and t equals 60 minutes. So I picked the point here, and I picked the point there. And so I've got my 2 time points. I just have to extrapolate to the y-axis to be able to get the speed at those points. And what have I done? So I've basically gone and I've said 15 minus 7. So I'm trying to keep the speed in the meters per second units, because again at 60 I've got a speed of 15. At 40, the reason I picked that is, again, it gives you a nice value. So you got 7 there. And I basically, so each of the units on the y-axis is basically 1 meter per second. And I've essentially converted the time in minutes into seconds. So I've got 60 minus 40. So that's a gap of 20 minutes, and I've converted that 20-minute gap into seconds. So multiplied it by 60. So that gives me a maximum gradient of 8 by 1200, which is 0.0067 meters per second squared, which is also around 0.007 meters per second squared. That's the maximum gradient, and that's also the maximum acceleration for the ship between these two ports. The next thing they want to know is the total distance traveled by the ship between the time of 42 minutes and 100 minutes. So we've got 42 minutes. So I've got the first black line, and I've got the 100 minutes. So these are the 2 points. The point here and the point there is basically where they want to know they want to know how much the ship has gone, essentially. So I want to make a quick correction there. So 42 minutes actually is a little bit earlier. So here in the time axis, each of the divisions is basically 2 minutes. So 42 minutes would be around here. Yeah, it's not around there. Sorry about that line if it caused any confusion. And you've got another dark line here at 100. There's a reason why we included the line at the 60. I'm just trying to split it up into a couple of shapes, just make it a little bit easier to work with. So the total distance traveled is the, if I want to get the total distance, the area under the graph between the two times that they've given. So the area under curve between t is equal to 42 minutes and t is equal to 100 minutes can be split into the area of the trapezium. So you're going to have a trapezium between the 42nd minute, which is going to be around here, and the 60th minute. And then you're going to have a rectangle between the 60th and the 100th minute. So it's going to be the area of those two, which are written out. And the area of the trapezium is half times base into the sum of the heights. And I have basically done that here. And that gives me around 13,500. Note that because I am multiplying, essentially, so I've still got my speed in meters per second, so that's 10 plus 15. But I've got my times in minutes, so I do need to convert the time into seconds. So that's why I've done it 60 minus 42 times 60. That is basically, you've got around 18 minutes here multiplied by 60 seconds per minute to be able to get the value in seconds, and that gives me 13,500 meters for the trapezium. And then for the rectangle, it's a little bit more straightforward, it's the length into the width, and we know that that is going to be 40 times 60. So that's fairly straightforward as well to be able to get the area of the rectangle, and that gives me 36,000 meters as an area. And if I add those together, then I get a total distance traveled of 49,500 meters. So again, it's very simple stuff. All you need to know here is that the area under the curve for a speed time graph is the distance. You've been given the two times, and the easy thing to do is to split it into shapes that is easy for you to work with. Again, the geometries are straightforward. You usually get either triangles or rectangles or trapeziums. That's usually what you'll be working with, sometimes a combination of them as seen here. And you just need to be able to obviously plug in the right values and just make sure that you are calculating the right things. So again, here I've done 40 into 60 because 40 is 100 minus 60, because you've got 100 minutes and 60 minutes, and then I just multiplied it by 60 to be able to get my seconds. So hopefully that makes sense. The other questions again seem to dive into topics that we're not covering in this video, so I am going to move on to the next paper. It's got two more to go. So we've got May, June 2020, looking at paper 43. So May, June 2020, paper 43. So they've started off with the question of define acceleration. Obviously, when I mentioned that you got to be able to describe scenarios with these different quantities, you also need to be able to define them. So acceleration is the rate at which an object's velocity changes, or you could just literally say acceleration is the change in velocity by time. They are more than happy to give you marks if you just put the formula in. That's probably the quickest and smartest thing to do, as I've done below. The next is a nice question asking you to describe the motion which is shown in each of these different graphs. And you've got a couple speed time graphs at the top, you've got a couple distance time graphs at the bottom. The key is to make sure that you don't get caught out by the fact that the top two graphs are different from the bottom two graphs, so just make sure that you pay full attention to that. So in the top graph, we got essentially we got a negative linear gradient. If it's negative, it's decelerating. If it's linear, which means it's got constant deceleration, it goes all the way up to speed of 0, which means it ends up at rest. So obviously that's constant deceleration is evident from the linear negative gradient and ends up stationary. And second scenario, you've got a positive non-linear rising gradient. So if it's positive, it's accelerating. If it's non-linear, the rate of acceleration is changing and it's rising, which means the acceleration is increasing. So the object is accelerating faster with time, as evident from the non-linear positive gradient, which is also increasing, or rising. Then you move on to distance time graphs. Now, it's important to remind yourself that the gradient is now the velocity. It's not the acceleration anymore. But if you look at C, you've got a positive, non-linear, flatlining gradient. So if it's positive, that means the distance is increasing, so there's a constant speed. If it's non-linear, the speed is changing, because that means, if it's non-linear, the gradient is changing, the gradient is the speed, so the speed is changing, that's the acceleration. But essentially the object is flatlining, which means at some point it's going to reach a certain distance away from its source and it's going to stop. So object is accelerating till it reaches a constant speed towards the end, as evident by the positive nonlinear gradient, which is gradually declining. And the final scenario, you just have a positive linear gradient for a distance time graph. So positive means moving away from the source. Linear means it's a constant gradient, which means it's got a constant speed. So that's what that means. It's a nice and easy question. How many marks was that? So you got 1 mark for the definition. Then you've got around 6 marks there. So 7 marks, nice and easy. All you need to do is just remember those gradients, and you should be good as gold. And the final one that we have is Feb-March 2020. The Feb-March papers are always variant 2, so you got 4-2. And here we have to do a bit of plotting. So let's have a look at this question. So a rocket is launched vertically upwards from the ground. The rocket travels with uniform acceleration from rest. After 8 seconds, the speed of the rocket is 120 meters per second. So you want to calculate the acceleration of the rocket. So the acceleration is a change in speed over the time. So I've got final speed minus the initial speed by time. So we said it starts at rest. So we have this information. And then it reaches a speed of 120. So that's final speed is 120, initial speed 0. And it does this over a time of 8 seconds. So it's got a speed of 15 meters per second squared. And then the next one is on figure 1.1, draw the graph for the motion of the rocket in the first 8 seconds. So that I've drawn, do mind my drawing, but that I've just drawn with the straight line here because we assume that there is a constant acceleration, as we've seen. And they say use the graph to determine the height of the rocket at 8 seconds. The height is basically the distance traveled. And we know that from a speed time graph, the distance traveled is essentially the area under the curve. So we've got here a positive linear gradient, which means we're going to get a triangle. So it's going to be half base into height. So again, if we go up to 8, 8 is around this point here, which I've got there. So that's around 8. And then if I look at the speed for it, we can see that the speed for that is around 120 meters per second. Again, if I multiply it out, it says I've traveled 480 meters in a matter of 8 seconds, which is pretty quick. And then they said from time t is equal to 8 to time t is equal to 20 seconds, the rocket rises with increasing speed but with decreasing acceleration. From time t is equal to 20 seconds to time t is equal to 25 seconds, the rocket has a constant speed of less than 200 meters per second. We want to draw the line. So again, please do mind me for my not so straight lines and not so great curves here. But yeah, in the exam, hopefully some of you will be a little bit more diligent in drawing a slightly better curve. But I think it paints a story here where if you start from 8 and go all the way to 20, it's still accelerating, which means speed is increasing, it's positive, but the rate of acceleration is decreasing. So you can see that we've got essentially a positive non-linear flatlining gradient. So we've got that. And then the end, we say it moves at a constant speed that's just slightly less than 200 meters per second. You got 200 meters per second there. That's essentially 200 meters per second right above the line. And we've got a straight section there from 20 to 25 seconds where it's just literally going flat. So hopefully that makes sense. And again, to be honest, I've not seen too many questions where you had to plot things on graphs. You usually had to just calculate things from graphs, like the use of gradients and areas. You haven't had to plot too much on graphs, but this was an example where you had to do that, so I thought I'd include it. So hopefully none of you get caught out having to draw a curve like this. So that was all the papers I wanted to look at in this topic. I hope the concepts that we looked at in the previous video made sense, and you can see them in practice in some past paper questions. Again, if you've got any questions or have any comments, please feel free to leave them in the comment section below. Again, if you found the content helpful and would like more such videos, please like, share, and subscribe.